Unit 3.1, Electric Charge. We're going to start by reviewing the Milliken oil drop experiment, which was performed in 1909 by Robert Milliken. He performed the experiment at the University of Chicago, where he observed the motion of tiny oil droplets between two parallel metal plates. The oil droplets were charged by friction in an atomizer. An atomizer basically is a perfume bottle that sprays an oil into tiny little droplets. The oil droplets were charged by friction in the atomizer and allowed to pass through a hole in the top plate. Initially, the droplets fell due to their weight. The top plate was giving a positive charge as the droplets fell, and droplets with a negative charge were attracted back upward to the positively charged plate. By turning the charge on the plate on and off, Milliken was able to watch a single oil droplet for many hours as it alternately rose and fell. This is a very difficult, physically difficult thing to do. He had to actually look through a scope to see this tiny little droplet of oil, and then turn. He would have to turn a plate or turn a switch to change the amount of charge on these two plates. After repeating this process for thousands of drops, Milliken found that when an object is charged, its charge is always a multiple of a fundamental unit of charge, symbolized by the letter E, which now we would call the electron. In modern terms, charge is said to be quantized, and E has been determined to be 6.02 times 10 to the negative 19th coulombs. Just a little demonstration of this. There's a site called OPhysics, which has some neat simulations. And here we've got a picture of the Milliken oil drop experiment. We've got a drop in the middle of the two plates. And I'm going to hit run. And we see that the droplet starts to fall. So I'm going to increase the voltage and decrease the voltage and increase the voltage until, let's see how close I can get, until I try to get it to just, well, you can imagine the tedium Robert Milliken went through to try to balance these charges. And he would record the voltage, and from the voltage, he could figure out the magnitude of the electric field, which is another thing we'll talk about. And he knew the approximate weight of each droplet, and he could use that to figure out the charge on the particle. Okay, so that's just a little simulation you can try. Again, it's at ophysics.com. So, what did he find? He found that like charges repel, and he found that the object is charged by the transfer of electrons. This is important because remember that the model of the atom, the Bohr model of a hydrogen atom, for example, would be a single electron orbiting the nucleus, which is a proton. Now, what we know is that it's not easy to break up the nucleus, but we can move the electrons around, and that's what we're going to see with static electricity. So electric charge is always conserved. It's transferred, not created or destroyed. So we're going to see that charge can be transferred between different objects. The electric charge is quantized. That means that it comes in multiples of the charge on one electron. And finally, the charge on one electron is 1.602 times 10 to the negative 19th coulombs. The charge on a proton, by the way, is the same. And a proton has a charge that is positive instead of negative. Okay, so the atom. So electrons are the negatively charged particles that are part of an atom. They're located on the outside of the nucleus and they move around it. Electrons are involved in bonds, and electrons can be transferred from one atom to another. One electron has a charge of 1.6 times 10 to the negative 19th coulombs and a mass of 9.109 times 10 to the negative 31st kilograms. Protons are positively charged particles that are part of an atom. They are also located in the nucleus. Protons have the same magnitude of charge as electrons. However, protons are much more massive than electrons, with a mass of 1.673 times 10 to the negative 27th kilograms. And finally, neutrons are neutral particles located at the center of an atom. They are located inside the nucleus with a mass of 1.675 times 10 to the negative 27th kilograms. Now, I would like to say just a note here. I'm going to go to PhET for a moment. I showed you a picture of the Bohr model of the atom. And I'd like us to think about, through history, how people have conceived of the atom. And I'm looking for models of the hydrogen atom. I guess I'm going alphabetically. Here it is. So one thing that's really neat is somebody figured out how to take these Java applets and change them so that they are usable on an iPad. So it just takes a moment for it to load. Powered by Chirp. All right. So we just have to be a little bit patient. Okay. So in this applet, they show us, it goes all the way back to the billiard ball model of the atom. You may remember that. And then plum pudding, and then the solar system model, and now the Bohr model, where we have the nucleus, and then we've got electrons rotating and at fixed orbits. Later, we learned about the de Broglie model, and then finally the current, or closest to the current model, the Schrodinger model, which says that there are orbitals that are basically probability clouds. And if I shine light on this atom, what will happen is the electron will go to higher energy levels, or it will give off a photon when the electron drops down to a lower energy level. We're not going to talk about this stuff until we get to Unit 7 when we talk about atomic and nuclear physics, but I just wanted to remind us again of these different models of the atom. Right now, I'm using the Bohr model, where the atom has a very fixed orbit. So it's kind of a simplistic version. Anyway, that's what we have in the picture here. Okay, so what happens when we strip or add electrons to an atom? We know that atoms can become ionized. And here I've got some examples of, what would happen if I had 5 negative and 5 positive charges. Well, it's not that I wouldn't say I have no charges, because I don't have no charges. I have 5 negative, 5 positive. But I do have a net charge of 0. In other words, the positive and the negative cancel. These are pretty simplistic examples, but here's another one. I've got 3 negative and 5 positive for a net charge of +2. And finally, 5 negative and 4 positive, I have a net charge of -1 electron. So we want to, again, think about net charge. It's not that we ever have 0 charge necessarily, but we can have charges that balance through ionization. Okay, so let's look at some different situations of how charging can happen. First of all, we want to think about whether or not we're working with an insulator or a conductor. An insulator does not allow charges to move freely, while a conductor does allow charges to freely move in response to an electric force. Typically, conductors are metals, and insulators are usually organic, or things like wood, glass, things like that can be insulators. So when we're talking about charging in these examples, we are charging conductors. So let's say I start with a neutral metal rod. So if I could zoom in on this neutral metal rod, it's not that there would be no charge. The fact that it's neutral, oops, let me make this a little skinnier. The fact that it's neutral means that there is equal numbers of positive and negative charges in the atoms bound inside of that rod. Okay, now if I had another rod, this one, oops, that had a net positive charge on it, then what would happen is the negative charges on the original metal rod, so one of these, would be attracted to the other rod, and the negative charge could leave. Now, it's only the negatives that can move, because only the electrons on the outside of the atom are free to move around. The protons cannot move. If you try to move protons around, you get an atomic, you get fission, and that's an atomic bomb. So we don't want that, at least not for this unit. Okay, what else can we do with this kind of situation? Let's say, again, that I've got a neutral metal rod. So let's say, again, remember that neutral means that there's equal numbers, positive and negative, and hopefully they would be kind of nicely spread out here. And then what I do is I bring in a positively charged rod. And what's going to happen, again, is the electrons are free to move. So those electrons that were free to move are going to be attracted to the positively charged metal rod. Now, this is induction. They're not actually touching. So no charge is actually transferred. So what happens is the negatives move to one end, leaving a net positive charge on the other end. If I took this positively charged rod away, the neutral metal rod could return to its former state. In other words, the negatives could spread out evenly. And remember that all of this is based on the idea that like charges repel and opposite charges attract. So like charges repel, opposite charges attract, and the electrons are free to move. Okay, so this is actually an example of what we call polarization or charge separation. On the right here, we've got an example of charging by induction. And in this example, we start again with a neutral metal rod. So this one is neutral. And this symbol means that it's connected to ground. And the ground is basically an infinite well of both positive and negative charges. But remember, only the negatives are free to move. The protons are trapped in the nucleus. So now what happens is if I bring a negatively charged rod near, then the electrons, the electrons that were formerly spread out, they're going to be repelled. Oh goodness, hang on a second. Let's see if I can animate this a little bit. Okay, they're going to be repelled. So this negative charge is going to be pushed away from the negatively charged bar. So, and it has a path to get really far away. The charges want to spread out. The like charges want to spread out as much as possible. So this negative charge is repelled by the negatively charged bar, and it's got a path to ground, so it's going to be able to leave. And what happens when these negative charges leave is that we are left with a net positive bar. And this process, again, is called charging by induction. Okay, let's try an example question. A suspended object A is attracted to a neutral wall. It is also attracted to a positively charged object B. Which of the following is true about object A? Okay, so object A is attracted to a positive object. So we know that object A has to have a negative charge. But let's take a look at how this can be. How can this object be attracted to a neutral wall? We've got an animation in PhET. Here we've got a neutral wall on the right, a yellow balloon that is neutral, and a sweater that is neutral. And what I'm going to do is I'm going to rub the balloon on the sweater and pick up these negative charges. Now the balloon is negatively charged and it's attracted to the sweater. And maybe you've had this happen in the winter time. Your hair might get staticky or your clothes might get staticky, we say, because it's got a net negative charge. It picks up electrons more easily in the low humidity. Now I'm going to put this balloon on the wall and watch what happens. See how the negative charges in the wall are repelled by the negative balloon? The repelling of those negative charges creates a polarization in the wall. Polarization meaning that the positive and negatives are split. And now the negatively charged balloon is attracted to the wall because the surface of the wall has become positively charged. So that is a neat thing for you to play with. All right, that is the end of our notes for section 3.1. We will take a look at the sticky tape lab, and hopefully you'll have an opportunity to try some of these properties out for yourself, like that like charges repel and unlike charges attract. I'll talk